Welcome back, learners. In the first part we had discussed about the aromaticity in heterocyclic compounds, especially aromaticity properties in thiophene, pyrrole and furan, and we have seen how the pi excessiveness or the number of electrons present in the heterocyclic rings are cause of aromaticity in the heterocyclic compounds. Learners, the lone pair of electrons present in the orbital of, or we can say present on oxygen in case of furan, on nitrogen in case of pyrrole, and similarly on sulfur in case of thiophene are the cause of aromaticity. Now, here in this part we will discuss how the aromaticity affect the reactions of aromatic compound. How can we describe the reactivity of these heterocyclic compounds and which type of reactions these heterocyclic compounds gives. So, we will discuss here electrophilic substitution reactions given by these pyrrole, furan and thiophene. And aromaticity order. What is the aromaticity order in case of these three heterocyclic compounds? So, aromaticity order on the basis of delocalization of pi bonds, and also very important point, learners, it is based on this aromaticity order can be explained on the basis of delocalization of pi electrons, also availability of lone pair or non-bonding electrons which is present on the heteroatoms. So, on that basis the aromaticity order is sulfur heterocyclic compounds are most aromatic, then nitrogen, then oxygen, because oxygen is the most electronegative, and if this is the most electronegative, it will hold the lone pair of electrons tightly, will not take part in delocalization easily as compared to the lone pair of electrons present on sulfur and nitrogen. So, it is very important here, higher the bond electron activity or bond electron negativity, greater hold of lone pair of electrons by the heteroatom and more alternation takes place. So, it is very important point, you have to understand the aromatic characters is depends upon the delocalization of pi electrons or also the availability of lone pair of electrons which is present on the heteroatoms. This case the bond alternation ratio in C2 and C3 and C3 and C4, if R equal to 1, so the compound will be aromatic. It is very important. So, you have to understand if the bond the ratio, that is the R, value of R is a bond alternation value. So, how you have to calculate the bond alternation value and how will you find out the compound is aromatic or not, right. So, this is for every aromatic compounds. If the value, that is the bond alternation value or bond alternation ratio, if the R is 1, then compound will be aromatic. Like in case of thiophene, it is R value is 0.964, in pyrrole the R value is 0.959 and in furan the R value is 950. It means that the furan is least aromatic compounds in these three heterocyclic groups. Now, again the high electron negativity, oxygen, nitrogen, then sulfur, strong attraction on lone pair of which restrict the lone pair up to some extent to take part in delocalization, right. So, de-shielding and shielding characteristics in NMR spectra also confirms the aromaticity order. Ring currents effects also observed in some ratio. So, these factors also prove the thiophene, pyrrole and furan. These are the aromaticity order in 5-membered heterocyclic compounds which contain sulfur, nitrogen and oxygen in them. In 5-membered aromatic heterocyclic compounds, carbon signals. So, we can see carbon signals at between the 100 and 150 ppm, and it means that will be the, we can see more shielded positions. Similarly, in C13 NMR C13 spectroscopy, the shielding of ring carbon atom is proportional to the pi electron density. Or another factor we can explain on the basis of dipole moment. The magnitude of and direction of the dipole moment depend upon the resultant of inductive effects, because there is also inductive effect due to more hetero electronegative atom on pi bonding electrons. So, pi, there are two types of effect operates here, learners. In these 5-membered heterocyclic compounds, two types of effects operates here. One is inductive effect, another is mesomeric effects. So, inductive effect due to presence of the sigma bond and mesomeric effect due to presence of the pi electrons pairs. So, inductive effect is superimposed by mesomeric effect due to involvement of pi electrons. So, these are the three structures you are looking on your slide on your screen. One is tetrahydrofuran, tetrahydrothiophene and tetrahydropyrrole. So, there is a large difference in the thiophene because the involvement of d orbitals. So, we can say here large mesomeric effects can be seen in case of thiophene. That is why thiophene is the most aromatic in that heterocyclic compounds. So, you can see the direction of the dipole moment. Direction tetrahydro heterocyclic compound, that is the non aromatic compounds, is downwards, while here in upwards, right. So, two types of effect, one is inductive effect, another is mesomeric effects. Learners, here in benzo-fused 5-membered heterocyclic compound, that is a indole. Indole, here fusion of benzene to 5-membered ring which reduces the aromatic characters. So, it is very important. If in benzo-fused heterocyclic compounds, if there is a benzene ring, due to presence of benzene ring, it reduces the aromaticity. Nearly planar, which shows the bond alternation and more than one. So, R value is more than 1 here, it means that lower degree of aromatic character. Similarly, this is here benzene ring is fused across the carbon-carbon. You can see here there is a pyrrole ring which is bonded or which is fused with 2 carbon atom. So, here again aromaticity further reduced due to considerable degree of aromatic character. So, in that 5-membered fused heterocyclic compound, benzene thiophene, benzene B pyrrole, that is indole, and benzene B furan, it is the aromaticity order. So, always remember, higher the electronegativity effect, lower the aromaticity character. So, as the electronegativity increases, the aromaticity of heterocyclic compounds is decreases, because the availability of lone pair of electrons in the ring is decreases. That is the main reason. Similarly, this is another example here, the lone pair of electrons not involved, destruction of 6 pi electron system in the benzene rings. Indolizine, another, this is bridged nitrogen atom which influence the aromaticity character, electron rich pyrrole and electron deficient pyridine, and here is a resonating structure which decreases the aromaticity in this fused benzo fused hetero aromatic compounds. These are the two another examples, carbazole and dibenzothiophene. So, here also you can see here there is a benzo fusion of 2 benzene ring, right. on the both side of heterocyclic ring. So, fusion of second ring, that is benzene, to the benzo fused heterocyclic reduces the aromaticity. Resonance energy also evidence the low aromatic character of in these compounds. Learners, now here question is arising here, which type of substitution reactions given by heterocyclic compounds and at what carbon atom, right? Because there is a 4 carbon atom and 2 pi bonds and 1 lone pair of electrons, total 6 electrons takes part in bonding delocalization of electrons. So, 6 electrons distributed over 5 sp2 hybridized atom. So, question is arising here, why aromatic compound, that is especially heterocyclic aromatic compounds pyrrole, furan and thiophene gives electrophilic substitution reaction over the addition reactions, because here these are characterized by their ability to undergo electrophilic reactions. Substitution reaction takes place on the carbon rather than the addition. So, here that substitution reactions, electrophilic substitution reaction takes place on the carbon atom, not heteroatom. Here you can see in the structure electrophilic attack on the ring carbon, why the electrophiles attack on the ring carbon atom, and why these compounds gives aromatic electrophilic substitution reactions. What is the reason? Because you are looking here in your slide, as I told you in the previous, there is a 2 type of effects takes place. One is inductive effect and other is mesomeric effect. So, mesomeric effect release from the heteroatoms, right. So, due to that mesomeric effect, the heteroatom bears that positive charge, that due to that lone pair of electrons presence on the heteroatom, it shows the mesomeric effect, and when mesomeric effect shows that heteroatom, that is nitrogen, that is sulfur or that is oxygen, that nitrogen, sulfur and oxygen bears a positive charge. What it means? What does it mean? It means that the electrophile, it hinders the attack of electrophiles to the heteroatom, because heteroatom is already electron deficient now due to mesomeric effects, and which facilitate the attack of electrophiles, right. So, positive charge on heteroatom hinders the attack of electrophiles. Only nucleophile can attack on that heteroatom, because nucleophiles are electron rich species. So, less reactive, these heterocyclic compounds are less reactive towards nucleophiles and are restricted to undergo deprotonation. What is the reason? Learners, as I told you, in case of pyrrole, especially pyrrole, because there is only one lone pair of electron present on the nitrogen atom. So, that lone pair of electrons mesomerically involved into the ring, right. That is why that pyrrole are aromatic in character, and due to delocalization of electrons, the carbon are having higher electron density, which facilitate the electrophilic attack on the carbon atom. So, that is the main reason. Now, it is in this slide you are looking here, there is a attack of electrophile at heteroatoms. So, here that are the alicyclic analogues of amines, ethers and sulfides. In that analogues, the electrophile can directly attack to the heteroatom, because lone pair of present on the heteroatom, that can be accepted by the electrophile. But in case of heterocyclic aromatic compounds, the lone pair of electrons present on the oxygen atom and 1 electron present on the sulfur atom in case of thiophene. Similarly, 1 electron present on the oxygen atom, only 1 electron pair are involved in delocalization. So, due to that delocalization, it increases the electron density to the 5-membered ring, which facilitate the attack of the electrophiles to the benzene ring. So, you can see here, this is the heterocyclic compound, right. So, here on each carbon atom electrophile can attack. So, right, because each carbon is having a high electron density due to involvement of bonding electrons. So, attack at the carbon atoms takes place. That is the reason why in heterocyclic aromatic compounds, the electrophilic reactions takes place at carbon atom rather than on the heteroatom. Now, if we will talk about here conjugated dienes. In conjugated alicyclic dienes, you are looking on your screen, there is a double bond, and along with the double bond there is heteroatoms. That heteroatom is X, can be oxygen, nitrogen and sulfur. So, in conjugated alicyclic, electrophilic attack on the carbon due to mesomerically electron releasing by the heteroatom takes place, and it resembles to the heterocyclic 5-membered ring. So, in that case, the electrophiles will attack on the carbon atoms and X becomes the positive. So, now as I told you, due to this aromatic character or involvement of lone pair of electrons within the ring in 5-membered heterocyclic compound which contain one heteroatoms, electrophilic substitution reaction takes place at carbon. But now question is arising here, at what carbon the electrophilic substitution reactions takes place. So, 5-membered heterocyclic compounds undergoes electrophilic substitution reaction at C2 and at C3, preferably at C2, because what is the reason why the reaction takes place at C2 and C3, or it prefers to the attacks take place at C2, because the transition states when the attacks takes place on C2 and C3 are stabilized and have a high electron density on carbon 2 and carbon 3. This is the C2 attacks. Learners, please see here in this slide, this is a electrophilic substitution reaction at C2. So, it is a C2 which is near to the heteroatoms. So, when you will attack or the reaction takes place at C2 carbon atom, delocalization, during the delocalization we get a negative charge, on that negative charge having a electron density. So, first attack over here we get a due to higher electron density on C2 or C3, electrophile attack on that carbon atom. After that deprotonation takes place, removal of a proton takes place, and we get a substituted electrophilic addition product. Now, C3, this is the attack at C3. C3 attack, if we talk about the C3 attack, now what is the difference over here? On carbon 3 attack, the reactivity is directly proportional to the electron availability on the ring, right. So, because here it's when here at C3 carbon atom, this is also higher in electron density, but mesomerically the C2 is higher electron density, have higher dense, right. So, it prefers the electrophilic substitution reaction prefers at C2 carbon atom. Reactivity depends on towards the electrophilic substitution reactions on the electron availability on the ring. It is also mesomerically electron release from the heteroatom. So, greater the stabilization, greater the transition states. Understand this, greater the stabilization and greater the transition state, and it facilitates the attack of electrophiles at that carbon atom. So, order of reactivity in case of pyrrole, furan, thiophene and benzene. So, learners, it is in decreasing order. If we compare the reactivity towards electrophilic substitution reactions, benzene is least among all. In fact, benzene also gives electrophilic substitution reactions, but pyrrole is the most electrophilic substitution reaction than furan, thiophene and benzene. So, this is the reactivity order in decreasing order. This is the pyrrole and the reaction takes place at C2 carbon atom, and here greater electron releasing ability of trivalent nitrogen. So, here the nitrogen is having 3 bond. This trivalent nitrogen having greater stabilization, greater positive charge on the that tetravalent nitrogen atom. Here in case of furan, if we compare between the electronegativity in furan and pyrrole, oxygen, furan having oxygen as a heteroatom, that oxygen is more electronegative than nitrogen. So, whatever takes place, it wanted to withdraw the electrons because it is a more electronegativity, more electronegative than nitrogen. So, due to withdraws electrons, positive charge is radially accommodated by oxygen. So, less stable than pyrrole. So, that is why pyrrole shows are highly reactive towards electrophilic substitution reaction than furan. Now, in case of thiophene even less reactive than the furans towards the electrophilic substitution reactions, because the sulfur atom is less electronegative than oxygen and it withdraws the electrons less radially from the ring from the carbon atom which is present on the 5 membered rings. So, mesomeric effect of sulfur is smaller than the oxygen. So, because of not effective overlapping of differently sized p orbital of carbon and sulfur than in carbon and oxygens, right. So, these are the important few notes you have to understand, you have to learn. Electrophilic substitution in thiophene is much easier than in benzene. If we talk about the bromination, you can understand this. Bromination in case of thiophene is 10 to the power 9 times more rapidly than the benzene. Also, it is a more reactive between the 10 to the power 3 to 10 to the power 7 than the pyridine. Benzene, then 5 membered rings of heterocyclic compounds which is having one heteroatom. So, benzene is less reactive towards electrophilic substitution reaction if we compared with 5 membered heterocyclic compounds which contain one heteroatoms. Because greater stabilization, what is the reason why benzene is less reactive towards electrophilic substitution reaction than aromatic heterocyclic compounds which contain one heteroatom, that is pyrrole, thiophene and furan, because greater stabilization energy in case of benzene having greater stabilization of energies. So, it is directly related to the higher energy of transition states which shows the lower reactivity. So, here you can see in the electrophilic attack in case of heterocyclic compounds which having heteroatom. So, this is the case of pyrrole which is having a nitrogen atom. Now, stability order in transition states, here this is a structure we are having CH double bond CH2 along with the NH2. So, learner, you can see here there is a involvement of pair of electrons. First electrophile will attack on over here, we get a positively charged carbon atom, and after that the nucleophile will attack over here. So, this in this conjugated system the reaction completed in 2 steps, one is electrophile attack, second is nucleophile attack. But in case of this heterocyclic compounds which contain nitrogen, sulfur or oxygen, the reaction completed in one step. In pyrrole, furan and thiophene, higher reactivity is due to unsymmetrical charge distribution. So, there is a unsymmetrical charge distribution. You can see the resonating structure of benzene in furan, in thiophene and in pyrrole. So, carbon atoms are high electron density in each case. So, if we talk about the mechanism, so mechanism of electrophilic substitution reaction in these compounds are similar to the benzene: attack of the electrophiles to form a sigma complex, loss of a proton, formation of substituted products. So, 5 membered which contain one heteroatom, electrophilic substitution takes place at alpha carbon or C2 and C5, or similarly can be C3 and C4 positions on high electron density. So, in last I would tell you at what positions the electrophilic substitution reaction takes place. So, learner, it is important preferably at alpha position the electrophilic substitution reaction takes place, because at alpha positions 3 resonating structures we can get. So, attack at beta position, that is C3 and C4, that is that after that attack we get only one resonating structures, and the bond between C4 and C5 intact, double bond character between C4 and C5 intact mesomerically, do not take part in the delocalizations. So, this is the alpha position, that is C5 or C2, which is a more stable transition and there is a lower energy. So, the attacks takes place on the alpha positions, and this is the, you can see from the this energy level diagrams. So, reaction path versus energy, from this you can also see the attack at C2 and C3. When the attack takes place C2, we get a transition state which is a higher, lower in energy, but when the attack takes place at C3 carbon atom, we get a transition state which is in higher in energy. So, preferably we get a reaction at C2 carbon atom in thiophene, in pyrrole and in furan. So, learners, in this part we have learned what is the cause of aromaticity in heterocyclic compound and why these pyrrole, furan and thiophene gives electrophilic aromatic substitution reactions, and at what carbon, at which carbon the electrophilic substitution reaction takes place, and we have seen the most preferable attack takes place at C2 carbon atom or C5 carbon atom, that is the alpha position, because there is a greater stabilization takes place. The transition state we get here is a lower energy, resonance energy, and which facilitates the attack of electrophile at C2 carbon atom. Thank you.